Okay, here is a fluid mechanics question. It's about buoyancy. Two survivors of a shipwreck find themselves in cold ocean water and discover a rectangular wooden panel that can serve as a makeshift raft. The wooden panel has dimensions of 1.5 by 2 by 0.1 meters. So we're seeing that we're using meters and kilograms. Make sure that we have meters, kilograms, seconds as the MKS system. The first survivor, weighing 64 kilograms, climbs onto the floating panel. If a second survivor also wants to use the panel for flotation, what is the maximum weight the second person can have while ensuring the wooden panel remains partially above water? So we have static equilibrium, two people. And this buoyant force, we'll call it F buoyant. This is balancing the weight of the door and the people. So this is called Archimedes' principle. So we'll need the density of the water. We need the weight of the wood. So they give us density of the wood, the volume of the wood, and the first person. So the thing that is unknown is the second person. If we look at it as a free body diagram, so this would be the free body diagram. We have two people. You can call them Rose and Jack. The two people and this door both have the weight pushing down onto the water. You set up this free body diagram. We have all the forces acting on this. So we have weight of Rose. Let's say that is the 64 kilograms. We don't know what weight of Jack is, but we know what weight of door is, and we know that buoyant force is equal to the weight of water displaced by door, because the door is the only thing submerged. In the free body diagram, we also set up our coordinate system, so x and y, and then we're assuming that the weight of the people are right in the middle of the door, so there's no moment or overturning. It's pretty much this door is going to be in the water, and the people are in the middle. The buoyant force is acting directly opposite to the people and the door. We can start using this free body diagram. We'll do sum of forces in the y direction is equal to 0. It's in static equilibrium, first of all, meaning we're taking this door and we're seeing all the forces acting on it. So there is, we'll call it the weight of Jack, that is pointing down, and using our coordinate system that means negative. We have the weight of Rose pointing down. We have the weight of the door pointing down. Then we have a buoyant force pointing up, so we'll call it F buoyant equals 0, because the sum of forces equals 0. Nothing is moving. Now we can solve for the weight of Jack, which is unknown, using this equation. Well, we know the weight of Rose. The weight of the door, let's get that real quick. So W sub door, we have the wood density, and then we have the panel dimensions. So you do the volume of the door times the density. It should end up in kilograms. And then the density of the door is 700 kilograms per meter cubed. So all this meter cubed part, they cancel out, so you end up with your mass. So you end up with 210 kilograms. Okay, and then now let's find buoyant force. So to get buoyant force, we said that it's equivalent to the mass of water displaced by the door. So buoyant force equals, using this equation, we have the density of water times the volume displaced by the door. So density of water, we're using this water, and they give us the density of the salt water, 1030 kilogram per meter cubed, and we're multiplying this by the volume of water displaced by the door. We have the volume of water displaced by the door. It's 1.5 times 2 times 0.1, so that gives us 309 kilograms. But we want a buoyant force, so force is the mass times gravity. So it'll be times 9.81. Should have added that here. 9.81. Okay, the buoyant force is the 309 kilograms times 9.81 meters per second squared. That gives you 3031.3 newtons. So now we will solve for weight of Jack. So using this original equation over here, weight of Jack equals negative weight of Rose minus weight of door plus buoyant force. B-U-O-Y-A-N-T. Wow. For the weight of the door, I forgot to do 9 times 9.81. So that means we have negative weight of Rose, which we said was 64 kilograms, times 9.81. 9.81 minus 210 times 9.81 plus 3031.3. Solving that, we get 343.36 newtons, and dividing that, so that's weight of Jack. Weight equals mass times gravity. The actual mass is going to be weight divided by gravity, so that's the 343.36 newtons divided by 9.81. That gives us 35 kilograms. So weight of Jack, he has to be 35 kilograms or 77 pounds. If he weighs 77 pounds or exerts that much force on this door, it'll be in static equilibrium. So with Archimedes' principle and fluid mechanics principles, the door will float, but if he weighs more than 77 pounds, the door and all the people on it will sink. So the answer, again, you use static equilibrium, and you end up solving for the weight of the unknown person.